Hello, in this video I'm going to solve the following problem for you. Probability theory, probability distribution function. Let x and y be independent random variables, both in 0 and 1 distributed. Standard normal distribution. Determine the distribution function of x over y. Pause the video at this point and give it a try. Okay, I will solve this problem in two different ways. In method 1, which is not the most efficient way to do this problem, I just want you to use the definitions of the distribution function and cumulative distribution function. Okay? This is by no means the most efficient way of solving this problem, so if you're not patient to see this solution, please feel free to fast forward or jump to the point that I start the second solution. If of course this problem is given to me in the exam, I will never do this using the first method. But being able to do this from first principles, I think will deepen your knowledge overall in mathematics, and it is very interesting. And of course you will definitely appreciate the effort of mathematicians to discover or develop new theorems that can do things more efficiently. Okay, so I will do the first method. I think it will also teach you a lot if you are of course interested in deepening your knowledge in mathematics. So let me start writing method 1. Just using definitions, yes. Okay, so the standard way when you start studying probability, when you want to find a probability distribution function of a variable, so in this case I want to find f, little f I will call it from now on. This is the distribution function of x over y. If I want to find this, and you know that x and y here in this case are continuous variables, so what I will do, I will first calculate the cumulative probability function, which from now on, by the way, I will call this little f and I will call this capital F. You need to calculate this, for example, at a number here, and then when you have this, in order to find little f of that variable at the same point, you have to differentiate your capital F with respect to its variable. So if you have a continuous random variable, this is the standard method that when you start studying probability, you learn how to do it, okay? And then you also need the definition of this capital F, which by definition is the probability that your random variable here, x over y, is less than or equal to a. Okay, so this is what I want to calculate. And then if I succeed to calculate this one, then I use this formula and calculate the little f, which is the goal of this exercise. Okay? Okay. So let us now start calculating this using this definition. So I will start here. Capital F of x over y at a is equal to the probability of x over y is less than or equal to a. And if I want to calculate this, because I have two random variables x and y involved, I have to take a double integral of the joint probability distribution, which we denoted by f sub x and y dx and dx dy on the domain D, but the domain D is actually all ordered pairs x and y in the plane, on the plane, such that x over y is less than or equal to a. Okay, for the definiteness of discussion, I will consider that this a is positive. Of course, you have to also consider other possibilities for a, and then the problem will be finalized. And that is why this method is not the most efficient way to do it. Okay, but because I just want you to give you the feeling of how to calculate things based on definitions, so that you can appreciate the theorems that makes it possible to do it more efficiently. So I just want to consider a positive, okay, and then if you are interested, you can solve it for other a's in using this method yourself. Okay, the first thing that you need to do is that, okay, what is this joint probability distribution here? Because in this problem they have mentioned that the random variables x and y are independent, so then it means that f of x, y, x, y can be written as the product of marginal distributions, f sub x, x multiplied by f sub y, y. Okay, but that's no problem, because this is given to us, this is given to us. How? They have told us that x has the standard normal distribution. So what does it mean? It means that f sub x, x is equal to 1 over square root of 2 pi e to power minus x squared divided by 2. And they also have told us that y is also the same, has the same distribution. So this also means that f sub y of y is equal to 1 over square root of 2 pi e to the power of minus y squared over 2 for x and y real numbers, any real number. Yes, that's the translation of this part of the assumption. So we have this and we also have this. So this means that I multiply these two and I will get this. How can I do that? Because this is the assumption in the problem that these are independent as well. So I put them here and I try to calculate this double integral on this domain. Okay, and then you probably have to remember what you learned in multivariable calculus. When you want to calculate double integrals, it is important to have the picture of the domain in front of you so that you are not mistaken. But that's what I'm going to do. So I want to visualize this on the plane as a picture so that I can use it and solve this integral. Okay, so if I want to draw some pictures here, this is what we have. Okay, so let me explain that. So this is the normal coordinate system, and you know that this x over y equals to a can be written in this form, and this is completely clear. It's a straight line passing through the origin, and because you see that now why this is important to assume that a is positive, because if a is positive, the slope is positive, and then the line will be of this type. But if a is negative, the line will be of this type. Okay, so then of course you have to solve the problem for that case as well. Okay, but now the point is that here we are interested to know x over y is less than or equal to a. Okay, so that's the line that x over y is indeed equal to a. But if I want to have x over y less than a, then I have two regions. One part will be this one, and the other part will be this one. So convincing yourself of this one is not hard. Okay, so I want to have x over y less than a. So let me just hatch this, highlight these regions. So this is one part of the plane that satisfies x over a less than or equal to a. And there is another part of the plane that satisfies the same condition, and it is here. So, and if you don't mind, let me call this one domain D1, or whatever you want to call it, domain D2. But what matters here is that the domain that I wrote here is the union of these two domains, D1 union D2. So this means that here, this domain of my integration is D1 union D2, and they don't have any overlap. And there is a theorem in multivariable calculus that will allow you to write this one single double integral as the sum of two double integrals, one on D1 and the other one on D2. So if I want to summarize everything here that we have, I can write f of x over y at a is equal to a double integral on d1 union d2. Okay, and then if you don't mind, let me multiply them, because this is this product. If I multiply this by that, I will have this multiplied by that will give me a factor of 1 over 2 pi, which is a constant. I pull it out, and then this multiplied by that, yeah, you can just write it as e to power minus x squared over 2 times e to the power of minus y squared over 2, and I have dx dy. And because of that theorem, I can split it into two double integrals. So the integral on d1, and then you have minus x squared over 2. Let me just copy and paste everything fast. Okay, so now I need to move these to the other page and calculate these integrals and add them up, and then we are done. Okay, so let me take the pieces of information I need for to the next page. Okay, so everything we need is here. So, and I have to calculate these two integrals. So let me call this integral I, and let me call this integral j. And here we want to calculate I first, okay? So in order to calculate a double integral, first you have to make your mind about which variable I have to choose as my free variable. Okay, so be careful. For integral I have this as my region. Okay, so if you look here, let us give the role of independent variable to x here. It doesn't matter which one. You can also feel the symmetry here. So what I'm saying is that for d1, x, the lowest possible value for x when I am in domain d1 is 0, yes, and the largest one will be infinity, because you see that the x's will increase infinitely without bound. Okay, so this means that if I want to calculate integral I write integral dx, but the integral goes x goes from 0 to plus infinity. Okay, and then what I have here is integral of e to the power of minus x squared over 2 times e to power minus y squared over 2, and then I have dy. But now I have to find the limits for y. So this you have to be a little bit careful. So choose one of those x's, for example, because we learned that x goes from 0 to infinity. So let us assume that this is one of those x's. And then I have to find the cross section of this vertical line with my domain. Okay, so and then you see that for this particular x in this range from 0 to infinity, the lowest possible value of x is here. The highest value for x is infinity, of course, because this blue region will continue forever. And if I ask you what is the y-coordinate here, you will tell me the y-coordinate is 1 over ax. Yes, that's the equation of the line. So this means that the lower limit will be 1 over ax up to plus infinity. So this is how I have to calculate this integral. Okay, so if I want to do that, I have to calculate, because first of all, this is not a problem, because the variable of integration is y, so in principle this goes out. It can be considered as a constant, but if you're a little bit familiar with these integrals, you know that these are Gaussian integrals, and this function doesn't have any primitive function among the elementary functions. So that is not how I can do it. So I have to be more creative and find a way. But this is not an obstacle, or might be not an obstacle at this point. Do you know why? Because my goal is not to really calculate this, because my goal is to find little f. The reason I am interested now in capital F is that because after calculating it, I want to differentiate it. And then now I have this in the form of an integral, and I know that later I want to differentiate it. So might be I don't even need to calculate the integral, because differentiation of an integral reminds you of the theorems that you have in calculus for differentiating integrals. For example, one of them is the first fundamental theorem of calculus, tells you how to differentiate an integral. Okay, so even though technically speaking it seems a dead end if I really want to calculate capital F explicitly. This is more or less a dead end. I have to write it as in the form of an integral and leave it, because I do not have any primitive functions for these functions involved in this integral. But I know that later I am supposed to differentiate, so might be there is still a hope. So that's what I want to work on. Okay, so as I told you, this can be considered constant. I can pull it out from the integral. So this becomes integral from 0 to infinity, and then dx e to the power of minus x squared over 2. And what is left for me is integral of 1 over ax up to infinity, and I have e to the power of minus y squared over 2 dy. Okay, so we know that we are not able to calculate this integral explicitly because of this function here. But what we know that if someone is able to calculate this, at the end of the day, this will be a function of x and a, because you are integrating over y. This means that this value will not depend on y because you are integrating over y, but this will depend on this x and this a. Okay, so I think it doesn't hurt if I give it a name. So I don't know how to calculate this explicitly, but I know it's a function of x and y, so let me call it phi of x and a. Sorry, it's a function of x and a, so I can call it phi x and a. And now what happens if I continue, this becomes integral from 0 to infinity, and then I would write phi x and a here, e to power minus x squared over 2 dx. Okay, so this is the most I can do for calculating I. I cannot go forward more than that. Okay, but now let me consider what happens to j. Very similar argument, so I will go a little bit faster. But be careful here, when you are on domain D, the highest value for x is 0, but the lowest value will be negative infinity. So if I make my mind to start with dx, so I would write dx, but I go from minus infinity to 0, and then I will have this same function dy, but let us consider the appropriate limits this time. So choose one of these x's. So let me change my color. For example, let me have this. Let us say that x is somewhere here. But then what happens here, if I look at this cross section of this vertical line, you see that the lowest y value for this particular s is negative infinity. But the highest value is this one, which exactly follows the same rule. Yes, so this means that I have to write it from minus infinity up to 1 over a x. Okay, and let's make this story short because that's exactly the same thing. So I would write it as minus infinity to 0, and I have dx e to the power of minus x squared over 2, but then there will be another integral that I am not able to calculate explicitly. Yes, but if you don't mind, let me give it a name again for the same reason. This is just a function of x and y, so let me call it this type of phi x and a. So finally, what do you have? You will have this equals to integral from minus infinity to 0, and then you have e to power minus x squared over 2 phi of x and a, and then you have dx. Okay, so I was able to show that integral I was not able to calculate it, but I was able to show that this integral can be written in this form, in which this phi is a function of x and a, and the second integral can be written in this form, in which this phi is also a function of x and a. Okay? Okay, so let me write it like this. So let me take this off and write this means that j is equal to that. That's a better way. Okay, but now let me also write here what do we have here. So I have f, capital F of x over y at a is equal to 1 over 2 times I plus j. Yes, 1 over 2 pi, sorry, I plus j. Okay, and now you know that my goal is to differentiate this function with respect to a. So it means that if I am interested to calculate little f of x over y a, this becomes d dA of capital F of a, which means that I have to write 1 over 2 pi d dA of I plus d dA of j. Yes? So I am calculating the derivatives of this. Okay, but let us concentrate on the derivative of I here. I have enough space. I think I will be able to do it. So this is your I. You want to differentiate I. So let me write everything explicitly. So d dA of I will be equal to d dA of that integral from 0 to infinity of function phi x and a e to the power of minus x squared over 2 dx. But then you know that we can flip this derivative inside, but I have to, because I have more than one variable there, I have to write a d partial derivative with respect to a of the whole combination of phi x and a e to power minus x squared over 2 dx, and then x goes from 0 to infinity. But now look, here I have to differentiate this function with respect to a. There is no a dependence here, so I can pull this out and I can concentrate on differentiating this with respect to a. So if I want to continue one more step, it becomes integral from 0 to infinity e to the power of minus x squared over 2 partial derivative of phi x and a with respect to a and dx. Okay? But now let me go and change my color here. So because my goal is to differentiate this with respect to a, and then what you see is you can use first fundamental theorem of calculus. But if you want to do that, you know that the main one, this function should be up there, so it is not there. But that's not a big problem because I can write a minus sign and flip these two. Okay. So somehow it needs a change of sign. So if I want to calculate, let me change this color here, dA of phi x and a, I will put a minus sign because I want to flip them, and then I have to replace the y variable with the lower limit, so it gives me e to the power of minus x squared over 2a squared, but I also have to multiply it by the derivative of this with respect to a, which is again minus 1 over a squared x. Yes, so that is the derivative. And then I plug that expression here. Okay, so then what happens? This becomes equal to it will be positive 1 over a squared coming out, and then it becomes integral from 0 to infinity x e to the power of minus x squared over 2a squared multiplied by e to the power of minus x squared over 2 dx. Okay, and then you can combine these two, so it becomes 1 over a squared integral from 0 to infinity x e to the power of minus, I can pull a 1/2 and x squared out, so it will be 1 plus 1 over a squared, just simple algebra, dx. Okay? Okay, now let me go to the next page. Okay, this is what we got, but now, because of the presence of this x, this integral can indeed be calculated. Yes? So for example, let me introduce a new variable. So let us say that z is equal to 1 over 2, 1 over 2, 1 plus 1 over a squared, x squared, then it means that dz becomes equal to 1 plus 1 over a squared x dx. So this means that x dx becomes equal to a squared over a squared plus 1 times dz, simple algebra. Yes, but then of course if x goes from 0 to infinity for my integral, this will also imply that z also does the same. Yes, because here z is a positive number multiplied by x squared. So if x is 0, of course z is 0, and if x is infinitely large, z also becomes positively infinitely large. So that's correct. And if I go back here, so I have 1 over a squared here, and then you see that instead of x dx, I can put this expression, but this is a constant. I pull it out, so it becomes a squared over a squared plus 1. And then integral, it goes from 0 to infinity again, and then I will have e to power minus z dz. Yes, but here this a squared and that a squared are cancelled, so I get 1 over a squared plus 1, and a primitive function for e to power minus z is minus e to power minus z, but I have to run it from 0 to infinity, but of course it becomes 1. If I put infinity, it becomes 0. If I put 0, it becomes 1. So finally it becomes 1 over a squared plus 1. So what I got is that dA of I is very simple, 1 over a squared plus 1. Yes, this is what we have. I don't want to calculate the second one. The second one is also very similar. Yes, so if I go back here, if I want to calculate the dA dj, this is your j, and the method of calculation is very, very similar. If you do the calculations correctly, you will get the same answer, okay? So you will see that dA of j will also be the same. Okay. Yes, and then you want to calculate little f. We had it before, yes? So little f of x over y of a is equal to, if I go back here, you see that I have it here, yes? Here. I calculated this, I calculated this, I have to plug them here, but of course I also have a factor of 1 over 2 pi, so it becomes 1 over 2 pi, 1 over a squared plus 1 plus 1 over a squared plus 1, so it becomes 2 over a squared plus 1, 2's are cancelled, so it becomes 1 over pi multiplied by this combination. So what we got is that at least I was able to calculate it for positive a, for negative a. Of course the domain will change a little bit, but the analysis will be the same, so I was able to get it here. And then you will see that you will get the same answer for every a, not just for positive a. So this means that this will be valid for a belonging to R. So the problem is finished, but some of you might recognize this distribution. That is the standard Cauchy distribution. So now we can say that x over y, of course that is not part of the problem. The problem is to find this function. We did it. But if you recognize this is familiar, which is famous in probability, we know that x over y is Cauchy with parameters 0 and 1. So that's the distribution of x over y. Okay, my intention here was actually to show you that, of course, from first principles, you still can do the calculations, okay? But I hope that you can see how complicated it becomes. And now we go to the second method, which is the efficient way and actually the good way to do this problem, okay? Okay, of course, before leaving this method, I just want to tell you that if you're observant, you really don't need to calculate the second part. You can anticipate that the answer to the second part will be also the same. So I'm talking about this. You really don't need to calculate this. Okay, let me tell you why. So let us go back here. And this is your j. You want to calculate the derivative of this one again. But you see that here, if I change x to minus x, okay, so here, let me first change y to minus y. And then what will happen if I change y to minus y, then this will go down with negative sign here. And then this will go up with positive sign, but this will not change because changing y to minus 1 doesn't affect anything. And then this function will be minus f of minus x. But then when you flip it here and do another change in x variable, x to minus x, then this limit will be from 0 to infinity, and this function will go back to this function. So it is very easy to see that, yes, by symmetry, if you have this argument, you could have anticipated that their values will be the same. Or if you are not happy with this, you can, of course, do the calculations explicitly. Okay, now we want to solve the problem in another way using the transformation theorem. But let me remind you the content of the transformation theorem only for two variables, okay? Because this can easily be generalized to any finite number of random variables. So what is the content? I would say that consider two random variables, x and y, continuous random variables, okay? But we don't have any other obligations on that. Let us assume that we also have access to the joint probability distribution function of these two, so we know that. And let us say that S is the support of this probability distribution. It means that it will vanish outside S. So S will be a region in the xy plane, okay? So let us imagine these things graphically. So let us say that this is the xy plane and S is somewhere, for example, here. This is my S. This is the support of this probability distribution. And now let us consider a transformation. I mean, two new random variables, which are functions of the old random variables x and y. So for example, I have u is a function of x and y. I'm a little bit abusing this notation. I'm using the same letter for the output and the name of the function, but I think it's understandable. So this simply means u is any function, not any, of course, well-behaved function of the random variables x and y, and we also have v equal to a function of x and y. Of course, this will define a transformation on this plane, so it will take the xy plane to what we call uv plane. Yes, let me call it here u and v. Under this transformation, we have changed, for example, this s to t. Okay, but of course, for this theorem to work, u and v should be 1 to 1, and also this transformation should be invertible. What guarantees that this transformation is invertible is that the Jacobian is actually not equal to 0. Okay, now the question is that if I know this probability joint distribution, how can I systematically find the probability distribution for these two new random variables? So let me write it in this form. Okay, and this theorem tells you how to do it. This theorem tells you that if you want to calculate this becomes equal to the function, probability distribution function for x and y that you have access, but then you have to replace x, so you can solve this and find x in terms of u and v. if this transformation is invertible. So you can write it as a function of u and v, and then you can write y as a function of u and v. Yes, so then it means that you have to write x as a function of u and v here, y as a function of u and v here, but of course you have to multiply by the absolute value of the Jacobian of this transformation. So here the Jacobian is defined to be partial derivative of x with respect to u, partial derivative of x with respect to y, with respect to v, and the partial derivative of y with respect to u, partial derivative of y with respect to v. You calculate this determinant. Okay? And then of course this is not determinant, this is absolute value. So this guarantees that this one that you are looking for can be calculated in this way. If u and v belong to the support t, this will become the support. So this t is the transformation of s under this transformation, which played the role of the support of the new variables, and of course 0 otherwise. So in principle this means it becomes 0 if u and v does not belong to t. So this will give you the probability, the joint probability distribution for your new variables u and v. So this is the content of the theorem that I want to use. Okay, so let us go to the new page and start solving the same problem using this method, which you will see is much more efficient than the previous method. Okay, so this is the content of the theorem that I explained briefly on the previous page, and now this is the problem. We know that x and y are independent random variables. Both of them are normally distributed, standard normal distribution. We want to find this. Of course, here in the main theorem I need two variables, u and v. But apparently here I have one new variable. Okay, the trick is to use one of the old variables as the other variable. So for example here, what I will do, I will introduce u, which is my focus, to be x over y. But for example, I introduce the second v to be y itself. Okay? And then what I need to do, I need to calculate this Jacobian, but it means that I need to express x and y in terms of u and v, which is of course very simple. So this means that y itself is of course v, and then if y is v, then if this y is v, then x becomes u times v. So then it means that x becomes uv. Okay, and now I can immediately calculate the Jacobian. So the Jacobian will be the determinant of the partial derivative of x with respect to u, which becomes v, partial derivative of x with respect to v, which this time becomes u, then partial derivative of y with respect to u, 0, and this one, 1. So if I calculate this determinant, it becomes v. Okay, something that's also very important. So in this problem, we know that x and y can take any values because this is the normal distribution, yes? So they can be positive or they can be negative. So it means that this new y, this new v can also go from minus infinity to infinity, and then u also the same, because I am dividing two numbers that are any numbers, so u can be in principle any number. Okay, so now I will start from here, and I would write f of u and v calculated at u and v is equal to f of x and y, and then I have to write x in terms of u and v, which is uv, and the other one is y, which is v, and then I have to multiply it by the absolute value of the Jacobian. So that is the content of the theorem. So this means that this function will be equal to this. But we know that x and y are independent. So this means that I can continue and write it as f of x of uv multiplied by f of y v, and then multiplied by the Jacobian, which was v. Okay, so but do you remember f of x is equal to 1 over square root of 2 pi e to the power of minus x squared over 2. So this means that f of x of u v becomes 1 over square root of 2 pi e to the power of minus u squared v squared over 2. And then we also know that the same thing for y, so I can write f y of v is just 1 over square root of 2 pi e to the power of minus v squared over 2. Okay? Okay, so then I multiply them. Multiplied by this absolute value, I will get my joint probability distribution. So this means that f of u and v calculated at u and v is equal to, if I multiply them, it becomes 1 over 2 pi. And when I multiply the exponents and factor minus v squared over 2 out, so it will be 1 plus u squared v squared over 2. Yes, and then multiplied by the absolute value of v. Okay, but you might say that, okay, I am interested in finding this function, not the joint probability distribution, but that is simple because now this can be viewed as f of u. This is the marginal distribution function, and we know how to go from the marginal distribution to the, we know how to go from joint probability distribution to marginal probability distribution by integrating over the other variable. So this means that what I am interested here, x over y calculated, for example, as at u, this is the integral of the joint probability distribution. So let me write it in this way for you. So this becomes equal to f of u, because that's the name I gave to x over y, and this becomes integral of f u and v uv, but integrated over v. Okay, but then I have to write the appropriate range here. But of course, for any chosen u, v can go from minus infinity to infinity. So let us just continue. So this becomes integral from minus infinity to infinity. And then instead of this function, I write this. And 1 over 2 pi is a constant. I pull it out. And then I have e to the power of, oh sorry, I forgot to put a minus sign here. Minus 1 plus u squared v squared over 2, and then absolute value of v, and then dv. So the only thing that now I need to do is to calculate this integral. But this is also simple because you see the symmetry on the variable. Whenever you have symmetry and you want to calculate, you always ask yourself if this function is even or odd. Because if it is odd, then the integral is 0, and if it is even, you can multiply it by 2, but instead go from 0 to infinity. And this is indeed the case. If I change v to minus v in my integrand, this will not be affected because of this even power. This will not be affected because of the absolute value. So yes, this function is even. So I can multiply it by 2. So instead I will have 1 over pi. But the integral will go from 0 to infinity. And then I don't even need the absolute value sign here, because on the interval from 0 to infinity, v is positive, which is actually a very good help. And then I have this. Yes. Okay, but this is a very simple integral to calculate because of the existence of this v, and the technique is the same. So let me go to the next page and calculate and finish the problem. Okay, but hopefully you can recognize that is the same integral I calculated in the first method at the very last part. But so how should I calculate it very fast? So I would write as z to be 1 over 2, 1 plus, I introduce a new variable, and then I calculate dz, which becomes becomes 1 plus u squared v dv. So this means that v dv becomes equal to 1 over 1 plus u squared dz. And of course, if v goes from 0 to infinity, the same will happen for z. Very simple to see. So this becomes 1 over pi, and then instead of v dv, I put this expression, but this is considered constant. I pull it out, so it becomes 1 over 1 plus u squared, integral from 0 to infinity e to the power of minus z dz, but that's exactly the same integral, and this result is 1, so this will be 1 over pi 1 plus 1 u squared. So this means that f of x over y calculated at u is 1 over pi 1 plus 1 over 1 plus u squared, and that is exactly the same result we got before. But you can see that this method is really more efficient than our previous method. But I also like the first method because it will allow you, it provides you an opportunity to actually think about the concepts you have learned in basic probability in a deeper way. Okay, so I hope that you enjoyed the video and it was helpful for you. Until the next video, be safe and goodbye. Thank you.